This video is made possible by our sponsors, Google, Vonage, and 8x8. See the video description for links and more information.
Okay, hi everyone. We're now in our first actual session of Cranky Geek 2020, and with me is Lital Mashiach from Facebook, who will talk to us about scaling Facebook video chat during COVID-19, and you're not a first-time speaker for Cranky Geek, so glad to have you here again.
Thank you. Hi everyone. So my name is Lital. I'm engineer manager in Facebook. I'm supporting the media team in remote presence org. And in this talk, I will share with you some of the challenges and solutions to scale our products with COVID-19. So in a very short time, we also launched a new product, Messenger Rooms, to be able to support better our users through these hard times. I will chat about the challenges in providing high quality in many different calling scenarios. It was a crazy journey for us the last year. I'm excited to share with you about that. So before I will talk about COVID-19, just a little bit where we were before COVID-19. So in Messenger, we launched audio calling in 2013, and then video calling in 2015. We also built the support of group calls. So we, before COVID-19, we supported group calls up to 8 people. Majority of group calls were 3-4 people. We also built some features like video effects, AR gaming, co-watch. 2019, we also launched our desktop native app. We worked on interop of calls between Messenger and Instagram. And then COVID-19 started. All of us went to work from home and all our priorities shifted. So let's talk about some of the top COVID-19 trends that we saw. So when the initial data started to come, it was very obvious that talk time is growing in all our video calling products in Facebook. So we saw that in Messenger, in Instagram, WhatsApp, Workplace, Messenger Kids, Portal, anywhere that we have video chat in one of the Facebook products, we saw this growth. So the trend was very obvious. It was very clear that something huge is about to come. One thing that was very interesting was the fact that group calling has been growing much faster than one-on-one calling. And that was very interesting, a new trend. In some countries, we saw a growth of 10x.
I guess that even made changes to how you had to think about video calling, right?
Yes, so people were starting to use video calling in completely different ways. Mm-hmm. So the patterns, usage completely changed. Another very interesting change was that we saw much more demand to large group calls. If till that point, majority of group calls were 3-4 people, very small groups, suddenly we saw people are using our products in ways that they were not using before. Our product limited group calls up to 8, and suddenly we saw those errors that people are attempting to add the 9th participant. So it was very clear that there is a demand for large group calls.
Mm-hmm. Interesting.
And another trend was the increase of usage for desktop clients. So mobile clients were always our main focus. And with COVID-19, we saw that web clients, the desktop native app, they are becoming a major client, major player. So all those key trends exploded during lockdowns around March and April. And then they settled above pre-COVID baseline in the new norm that we have right now. Okay, so with those trends, let's talk about the challenges that we had. So first of all, with this huge growth, first thing was just to make sure that we have sufficient capacity to support this massive growth in usage. And then the second challenge with this trend of large group calls, to be able to support large group calls. As I said, we were supporting till then up to 8 people. With the shift and growth of desktop clients to support large screens. This became a big focus area for us. And then to deliver high quality for different network conditions in these hard times when people are really relying on our products. Also, it became very clear that quality is what differentiates the different products in this market. So let's start with the first challenge to ensure sufficient capacity. So in Facebook, we are building our services to be able to handle those peak usage. So for example, in Messenger calling, New Year was always the day where we saw this peak in usage. But usually we have a lot of time to prepare for that. And this time, every day we had a new record. So it was really hard to prepare. We didn't have time to prepare for that. Also, all that happened exactly when the entire team went to work from home. So it made the challenge even more complicated. So what we started to do, we started to monitor very carefully all metrics, all trends, all movements, and try to see changes in behavior in different markets. So we will be able to scale our clusters to support growth in specific markets. We also work on efficiency for our media server, so we will be able to support more capacity. And another thing that we did, we built some knobs in our system. So if we are reaching our peak capacity, we will be able to reduce quality. So we add some knobs to temporarily downscale video quality or limit the number of video streams in a call, or to fall back to audio only if needed. So all of that were temporary knobs. So we will be able to make sure that we are dealing with this increase of usage. Okay, so next I want to chat about supporting large rooms. So we said rooms or large groups. Rooms is the product that we launched in a very short time. And with rooms, we increased the maximum people in call from 8 to 50. So one of the immediate challenges that we had by just increasing a number of participants from 8 to 50 was the fact that now we were sending many more media streams to the clients. And that became a problem. As we are increasing the media streams, the overall quality will go down. We are splitting the bandwidth with more media streams. So for video, it was less of a problem because our product, our mobile clients are showing the last 8 most dominant speakers. And for our desktop client, it is the 16. So the video streams are limited by design. The challenge was with the audio streams. So if we will keep sending 50 audio streams to each client, it will come on the expense of the overall quality. And we need to make sure that we are not increasing the minimum bitrate that is required with the group size. So what we did, we added a logic to the media server to cap the number of audio streams. So we build dominant speaker logic in the media server to detect the top K most dominant speakers, and then to forward only those audio streams to the client. One immediate problem that we saw when we did that was audio-video sync problems on the client. So if someone stopped talking, was pausing, and then starting again to talk, we saw these audio-video sync problems. That was a problem in WebRTC that we fixed. And by fixing that, it opened the door to leverage this feature where we are capping audio streams that we are sending to the clients.
Interesting. And what I see that you did things on the video side as well. It wasn't only optimizing audio.
Yes, great. So that was I will try to cover some of the top. We had many challenges. I was trying to pick a few interesting ones. The next one is video related. So the next one is performance problem that we immediately saw in our clients when we started to support large rooms. Pretty much, we saw performance problems in all our clients. For desktop, it was this fan noise. For mobile phones, it was battery consumption and devices that are getting hot. And pretty quickly, we saw that the video decoders are the top consumers of CPU. H.264 is something that we were using already on some calling scenarios, and it is well supported by hardware, but we had a few challenges with H.264 for large rooms. So the first one is that mobile devices, they have limit on maximum hardware decoder instances that can run in parallel. For new iOS devices, it will be 32. And there was no good mechanism to release decoders for tracks which are not active. So this is something that we had to build. So we built it into WebRTC, but it is more like a custom solution for our use case. Mm-hmm. So that opened the door to leverage H.264 on more calling scenarios and larger groups. And another challenge that we had was performance in Chrome. And there were like a few recent fixes that really opened the door to leverage H.264 more in Chrome. So the first one was assembly optimizations for OpenH.264 encoder in Mac. And the second one was a quality problem with H.264 where there was green video corruption, and that was fixed. And with those fixes and those changes, now we can leverage H.264 on many more calling scenarios, including large group calls. So the next challenge I wanted to chat about is keyframe control. So keyframes are important in order to recover from a bad state. For example, if there is a decode error or packet loss. So we need to resend keyframe in order to recover from that. And also for some necessary operations, like when a new participant is joining the call, or for simulcast layer switch. Mm-hmm. But the challenge with keyframe is that they are much larger than delta frames, and they might cause overshooting on bandwidth and network congestion, and in some cases, video freezes. So it is a problem if we are sending too many keyframes. The problem becomes much more critical in a large room, in a large group call, when it is enough to have one client in a bad state or in poor network condition to flood everyone with keyframe requests. So this is the challenge that we saw when we started to support large rooms. Mm-hmm. So in order to solve this problem, we had to do some work both on the server side and on the client side. So on the server side, we focused on improving the throttling keyframe mechanism in order to make sure that we are reducing those keyframe requests in the call. So what we did for the uplink, we started to consider both round trip time and frame interval before we are forwarding keyframe requests. So for example, for the scenario of screen sharing, frame interval might be much lower, and we should not forward keyframe requests the same interval that we are sending for other videos. For the downlink, what we did is to make sure that we avoid forwarding duplicate keyframe requests when we know that there is already keyframe in flight. So that was on the server side. On the client side, we also had to do some fixes. So one thing that we noticed was a bug in Chrome in simulcast. We saw that in the scenario of simulcast, with each parameter change, like bitrate or frame rate, there is a new keyframe that is being created. So we submitted an upstream fix for that. So that got fixed and reduced the number of keyframes. And the second thing that we identify is related to H.264. So in H.264, there is a feature to detect scene changes. What we saw is that this feature is too sensitive. So we are detecting H.264 detects scene changes also when nothing really major changed. And that just generates another keyframe. So that was a problem. And on our native apps, we disabled this scene change feature. Okay, so the next thing that I wanted to chat about is audio quality in fluctuating networks. So as I mentioned, quality is something that we really invested in the last months. So many users are relying on our products, and quality is really what differentiates the different products in the market. So I will cover 3 techniques for audio error resilience, and then I will talk about putting them all together into one solution. So I'll talk about in-band forward error correction, FEC, audio NAC, and audio redundancy. So let's start with in-band FEC. In-band FEC is a feature built in Opus, where a low bitrate redundancy frame is being added with the immediate following frame. And the main advantage here is very low overhead and low impact on latency. So for example, as you can see in the slide, if frame number 2 is lost, we will be able to recover it with frame number 3. So this technique is working very well when packet loss is low and when packet loss is uniformly distributed over the call. But as you can see, it will work less efficiently and it will be less effective when we have a burst of loss. For example, if you are losing packet 3, 4, and 5, we will be able to recover only the last packet, only packet 5. So this is one problem that we have with in-band FEC. So the next technique is audio NAC. With audio NAC, the receiver detects packet loss and sends a NAC request to the sender. And then the sender retransmits the requested packet. What we can do in the scenario of group calls, we can leverage the media server to maintain buffer of audio packets and resend from the buffer. So with that, we are reducing the round trip time and reducing the latency to resend the packet, but still there is a high impact on latency. And in some scenarios, the packet, by the time it will reach the receiver, it might be too late. On the other hand, there is the advantage of no additional encoding, decoding cost, and it is also compatible with web clients. The third technique is audio redundancy. So here, unlike NAC, the sender more proactively transmits multiple copies of the same packet. And again, it can be done on the server side with no additional overhead on the senders, on the clients. The impact on latency is much, much lower than NAC because proactively we are already sending duplications. On the other hand, there will be impact and high overhead on bandwidth and data consumption.
Okay, so we have these 3 techniques, each one good for something else. How do you decide what to use when?
Exactly. So this is the exact question to ask. So now the challenge is how to bring all of that together and benefit from the advantages and combine all those techniques. So first of all, when we identify that the network is lossy, we need to understand if the network is really lossy or congested. If it's congested, it might be the right thing to do to reduce the bit rate. And for that, there is also lots of investment in improving bandwidth estimation. But this is for now out of the scope of this talk. So assuming that we detect that the network is really lossy, how can we come with a unified approach that uses all those available techniques? So in order to do that, we need to understand what are the characteristics of the network and make the decision accordingly. So for example, we can look into packet loss. If packet loss is really high, as I mentioned, in-band FEC might not be effective. So it is better to rely on redundancy and NAC. If round trip time in the network is really high, NAC is not going to be effective. So better not to use NAC, better to rely more heavily on redundancy. But then if we know that the bandwidth is limited or the data cost is high, for example, if the call is on a cell, redundancy will be too costly. So better not to use redundancy and rely more heavily on other techniques. So this is what we are investing, and this is what we are doing. We are taking all those signals, and we are making a decision with dynamic and adaptive algorithms, what to use during the call. Okay, so I was trying to cover a few of the interesting problems that we've been working on in the last year to deal with the increased usage and increased demand with COVID-19. COVID-19 highlighted the need for human connection. We saw that in all our products. It really increases priority of products that bring people together virtually. We saw people using our products to celebrate birthdays, for baby showers, for weddings, for funerals. So the need to really focus on improving quality is higher than ever. We are still very far from real-life conversation quality. So we are just starting. There is a lot of work to do. A lot of interesting and exciting projects that are still to come. Thank you very much.
Thank you, Lital.
Thank you to our sponsors. Vonage, creating engaging experiences that move with your customers. See more at vonage.com/communications-APIs. 8x8, embed full-featured WebRTC meetings in your app with the Jitsi as a service beta. Sign up at 8x8.com/crankygeek. We would like to thank Google for supporting the WebRTC community and this event series. Learn more about WebRTC at webrtc.org.